In this video, I'm going to discuss the following equation. We are looking for real numbers x such that 10 to the power x plus 11 to the power x plus 12 to the power x is equal to 13 to the power x plus 14 to the power x. And we are given a hint that x equal to 2 is a solution for this equation that we have here. Okay, and now the question is find all real values x. We are given one solution and we are looking to find all of them. The key fact that's going to help us to find the solution is as follows. This is a simple fact. For a positive a to the power x is a monotonic function. Let me remove this point here. Is a monotonic function, right? So what exactly monotonic means here? The term monotonic. The term monotonic is definition. We call a function f from the set of real numbers to the set of real numbers monotonic if either for all x and y such that x is less than y, f of x is less than f of y, or for all x less than y, f of x is larger than f of y. So sorry, I shouldn't put equal to here, but you can also think about function that satisfy this property or this property. But here, by monotonic, I just mean the strict inequality to behold, right? And the claim here that I've made is that a to the power x is monotonic. So claim here a to the power x is monotonic. Why that's true? And to see the proof of this, remember the log function. Log function is defined on positive real numbers, right? Real numbers. So basically log is a function from r plus to r. And we know the simple fact that log is monotonic. In other words, so log is monotonic. In other words, we have log of x less than log of y if and only if x is less than y. So log is increasing and therefore monotonic. And so in order to show that, so therefore we have that log of f is uh, increasing. Log of f, instead of increasing, I'm going to use log of a is monotonic if and only if f is monotonic. So what's the proof of this? The proof is, suppose that log of f is monotonic. then for all x less than y, I know that log of f of x is less than log of f of y. This is one situation. The other situation is for all x less than y, log of f of x is larger than log of f of y. So if the first condition, if the first situation happens, so situation 1, since log is basically increasing, I know that if log of f of x is less than log of f of y, then f of x is less than f of y. And for situation 2, I have log of f of x larger than log of f of y, and therefore f of x is larger than f of y. So I have that thus one of these two is satisfied. F of x is less than f of y, or for all x less than y, f of x is larger than f of y. So therefore f is monotonic. So we prove that the log of f is monotonic if and only if f is monotonic. We had this claim here. Now I wanted to actually show that a to the power x is monotonic. And based on this little fact that we showed, thus to show a to the power x is monotonic, it suffices to check if log of a to the power x is monotonic. But what is log of a to the power x is x times log of a. Now if this is so we have two situations here. If a is larger than 1, then log of a is positive, and therefore x times log of a is increasing. And in the next situation, if x is if a is less than 1, then log of a is negative, and therefore x log a is decreasing. And of course, there is another case where a is equal to 1, and in that case, log of a is 0, and the function is constant. And x log a is constant. Okay, so let me put all of this here, and also this one here. Sounds good. So I have 3 cases. Okay, we showed that log a to the power x is a monotonic function depending on if a is larger than 1, then this is increasing. If a is less than 1, it's decreasing, and if a is equal to 1, it's a constant function. Okay, now let's go back to the original problem. The problem we had was 10 to the power x plus 11 to the power x plus 12 to the power x is equal to 13 to the power x plus 14 to the power x. Based on the fact that we just showed that both sides are increasing, right? But if left-hand side was increasing, and right hand side was decreasing, or the other way around, or the other way around, then we could easily conclude that this equation has at most one solution, right? And to see why, suppose that so here I have f of x equal to g of x, and suppose that this is increasing and this is decreasing. Then I have this increasing function, I have this is decreasing and the other one is increasing. So there would be at most one solution to this equation, to fx equal to gx equation. Here we have a similar situation. We have f of x equal to g of x, but the issue is that both sides are increasing, and I cannot use this argument. However, there is a simple trick to actually fix this, to actually bring it into the shape that we can actually use the argument I just showed you. 13 to the power x plus 14 to the power x. So both sides are increasing, but what if I divide both sides with 13 to the power x? What do I get in that situation? I would get plus 13 plus 12 to the power divided by 3, 13 to the power x is equal to 1 plus 14 divided by 13 to the power x, right? I have this equation here, and the point is that now the left hand side is, this is a decreasing function, and the right hand side is increasing. So now we are again in the situation where we have f of x is equal to g of x, where f is increasing, in this case decreasing, let's say decreasing, and g of x is increasing. And based on the argument I just showed you in the previous slide here, based on this argument, there is at most one solution. And the hint is giving us solution x equal to 2, and therefore that's the only solution we have. Thus x equal to 2 is the only solution to this equation. And that's a complete proof.